Very happy to introduce Daan Leijen. Daan has actually got his PhD from Utrecht University 2 years ago.
Yep.
And worked there as a postdoc. And he actually worked with colleagues of mine like Eric Meyer also at OGI, and has been at Microsoft earlier as an intern. And his latest work is actually on developing a language that has very few constructs, but that can orthogonality can be nicely put together to build really complex things, like the title says. And I look forward to your talk, Dan. Thanks.
Okay, thanks a lot. I hope everything works. Yeah, can everybody hear me? Yeah, great. So I'm Daan Leijen, and normally I'm a postdoc student in the University of Utrecht. It's a really small town in a really small country called the Netherlands. And now I'm visiting here for 3 months with Wolfram. And I've once been before at Microsoft, where people might still know me from, and I wrote the Babel package for Visual Studio to integrate languages. But today I'm going to talk about something more, I think, as practical, but maybe somewhat more esoterical. And it's called type inference. So what do I mean by type inference? Well, that means that you look at the program and you actually find out the type instead of the programmer specifying the type. So you're inferencing the types. So I'll give a little example there. It's a C# program which creates a list of integers, C# 2.0 with generics, and it adds some elements. And then if you would have type inference, you would get the second program. You just write new list and you add some number to it, and a type inferencer would see, well, there's a list being created, and because there's a 1 added, it's an integer, it's probably a list of integers. That's what type inference will do.
You probably want some marker saying that's a declaration and not a regular assignment, right?
Yeah, probably. Yeah, this is just, hand wavy about, this is type inference. I'm actually going to disappoint you more because I'm not really going to talk about C# type inference at all. I'm going to restrict myself to functional languages today. And actually, so I also put in a little Haskell fragment where you write the same list of integers in Haskell. And I'm going to use that notation for the rest of my talk, because I'm really going to talk about what are the limits of type inference. And type inference lends itself really well for functional languages. So that will be my vehicle today to explain everything. But what I really hope to show is that recently there's been a lot of development in type inference. And I want to show what those developments are and how the state of the art is right now. So a little bit more about type inference, why type inference might be nice, that I have normally this picture in my head. And on top of there are all programs, and you can write all programs in untyped dynamic languages, like Perl or Scheme or the Lambda calculus. And in a sense they're perfect. You just write your program, you don't care about types at all, and you can do whatever you want. And what are the not so perfect about is that you can do whatever you want, also not so good things. Make unsensible programs, add numbers and strings, for example. So there's a smaller set of programs, which are the correct programs. And really what you want is just stay within the correct programs. So we have, on the bottom line, we have what I call monomorphic programs, which are explicitly typed, like Pascal or Java. And they are always, in a sense, correct because they have types around them. But also a much smaller set of programs you can actually write as a programmer. So a bit better are polymorphic programs like Haskell and ML, and now actually C# 2.0 with generics or generic Java. And they're already something better, but there's a large class of programs that you can't really write in those as a programmer. And you want those abstraction levels.
So your slide seems to imply somehow that the set of explicitly typed polymorphic programs is a subset of the set of correct programs. Do you claim that?
No, what I mean by correct is sensible programs. And even the greater than, like what meaning do you attach to them, it's not like being Turing complete or anything. It's really expressivity from a programmer's point of view, what I'm talking about.
So a correct program doesn't go wrong?
Huh?
So a correct program is just one that doesn't go wrong?
Yeah, that's one that doesn't, for example, assign to a memory location an integer what's supposed to be a Boolean, or which doesn't, add apples to 4 hours. As we say in the Netherlands. Right? So that's my notion of correct program. It's not, of course, about logical errors that you might make or
Well, they're hardly important.
yeah, they're hardly important here. So that is really my mental model which I want to sketch here. And what the goal of type inference is really, I want to write a dynamic program. I just want to write the program, but still just get correct programs, programs that don't do nonsensical things. So type inference is pushing up from underneath to the correctness, while dynamic programs are out there. And it's soft typing that try to kind of push down.
Do you have any examples of things that one would like to write, but are by these lower levels that you're going to show? Because another way to say it is not that there's programs you can't write, but that the burden of writing them is lower if there's type inference, because the programmer doesn't have to sit there and state all these type declarations.
Yeah. So there's the advantage of not having to write types with type inference. So that's actually what I was going to say here, that Haskell is actually a programming language in ML that have type inference, so you don't have to write types. You can write a lot of programs with it. But there's still programs that you can write in explicitly typed languages like System F, and there's more you can write. So you can't really write them with type inference. And that's what I'm going to talk about today. So recently, there's been a lot of advancement that makes it possible to get on a System F, I will explain it later, level of expressing programs with type inference. And that's really coming close to probably all the programs you actually want to write in practice. So that's what I'm going to talk about today, how we can actually push the limit of type inference. And I'll show you, what the state of the art is there.
I have another question. So with polymorphic programs here, you actually mean parametric polymorphic programs, right?
Yes.
Because Java and object-oriented programs also consider to be polymorphic.
Yes, so I use the term polymorphic in the sense of generic in C# and Java, or parametric polymorphism if you want to be really precise. Sorry for the confusion.
Do you handle dependent types?
I'm coming to that. No, I don't. So I'm not going to talk about dependent types. Sorry, but there's lots of other stuff. So don't. Well, I would love to talk about it later because I'm really interested in it, like epigram. So to start with, the basics of type inference, I'm going to give a quick overview what that means and how most languages are set up today. And it's Hindley-Milner is really the mother of type inference nowadays, but it also has its limitations, and I'll come back to that later. But first, I'll sketch it. So Hindley-Milner is really the basis type inference system for ML and Haskell and Clean and basically any other functional languages out there. And there's a few nice properties, namely, you don't have to write any types at all. You just write your programs. And it will infer the types, and it does so efficiently and modular. And when there's something wrong, nonsensical going on, it will actually give you a nice error at compile time instead of at runtime. So here are a few examples that I've written down here of programs that you can write in most functional languages. Like I say that XS is a list of the number 1, or I give the definition of an increment function and the definition of an add function. So the increment function takes 1 argument, x, and adds 1 to it. And the add function takes 2 arguments and adds them together. Now type inference will automatically infer the types for these functions, and they're down here. So XS would be a list of integers. The increment function is a function from int to int. And we write it with a little arrow in between. There we go. And the add function takes 2 arguments and delivers an int. So we write it like that because of a lot of reasons, but mostly because you can partially parameterize the add function. Because in a functional world, functions are values too. So you can give 1 argument, and you actually get back a function from int to int. Namely, it adds what it increments by your first argument. So that's why. So you can also write these previous inc and add like this with lambda expressions. So that makes it more clear that functions are just normal values and not specially treated. So these are quite simple, but as soon as you want type inference, you actually need parametric polymorphism or generics. There's no way around it. So as soon as you start doing this, you have to go to polymorphic values. So I'll give examples of that here, because I can easily write programs like the above one. It's called the identity function, and it does nothing with its argument. So you give, it's an argument to the identity function, it returns the same thing, id x equals x. So what is the type of this thing? So you could say it's maybe from int to int, or maybe it's bool to bool, or float to float. But when you think about it, it's really, you can put in anything, and it will return something of the same type, the same thing. So here's where polymorphism comes in. So the type of identity is, for all types alpha, and whenever I quantify a type, for all types, I will use a Greek letter. So I say alpha to make it really clear. This is a function from that type alpha to alpha. So that's the polymorphism that comes in, or the generics of C#, or you can do the same thing with templates in C++. But as soon as you do type inference, even the smallest thing, you'll get to this. So you need polymorphism. And that's a big contribution of Hindley-Milner to give a whole system that takes care of this. So a few other examples, like single x, which puts a single argument x in a list. It's a singleton list. So it's a function from all alpha. Take some type, it will put that alpha in the list. So you get a list of alpha. And I've insert with appends an element to the list. So the strange operator here means append these two lists. Okay, so that's Hindley-Milner, and it actually works great. Like all functional languages have this underneath it, and I think they work really well. So you have a lot of abstraction suddenly to your disposition as a programmer if you can program this way. And also notice how lightweight it is compared to, for example, generic. So it's a nice, very nice way of writing programs. But there are a few fundamental things that are not supported by Hindley-Milner and not supported, therefore, by the main languages like Haskell and ML. And that's these two things. It's first-class polymorphism, which really means impredicative and higher rank, but I'll come back to that later. And the other one is first-class records and variants, which really means polymorphic and extensible. So these two items, I think, are really essential for doing proper programming. And I want to look in how you can actually add this to a language. I made a little experimental language called Morrow, which implements these things. Now that seems like something you should have done years ago because it's so useful. But actually, just recently, there was enough advancement in type theory to make this possible. And that's what I hope to explain later during this talk. So why is it important? Well, if you have these two features, Hindley-Milner plus first-class polymorphism, and you have first-class records and variants, you suddenly have a very small core language which you can really understand well. There's a whole lot of theory behind it. You have a lot of laws that you can count on, and it's very orthogonal features, but you can express a lot with it. So you have a small core language in which you can express many idioms that are usually encoded as special constructs. So it might be a vehicle of being an extensible language, a language that you can express lots of concepts that you would otherwise need special language features for. So one important one, I think, is first-class modules are essentially records with polymorphic values. And that's something you can't express yet in Haskell or ML because of these limitations. Another good example, which I can't go into here today, is the encoding of objects with records. That's something that Mitchell Want already tried to do, at least in the beginning of the 90s. And there were still a lot of issues with the first-class polymorphism. It kind of made the research stuck, but I think there's huge opportunities there. So I'm going to show an example of this actually here, because that's the easiest to show. Records with polymorphic values. I think that's something that's nice. So you can't do that yet in Haskell or ML or any other advanced functional language. And why not? Well, one of them is the records. All these languages don't support real first-class records as you would like to see them. And the other thing is polymorphic values. So in neither of these languages you can have polymorphic values inside structures. So they have polymorphism, but limited Hindley-Milner polymorphism. You can't put polymorphic values inside other components. And that's a huge technical problem, and I'm going to talk about it during this talk, how to solve that.
Question?
Yep.
I'm just easily confused. So the first-class module is going to be able to export polymorph values, but they're not going to be able to export types, right?
Yeah, so can you repeat the question?
Okay. They're going to be able to export polymorphic values, these first-class modules, because they're extensible. right?
Yeah.
But they're not going to be able to export types.
Okay, so...
Just to make sure I understand.
Okay, so I'm not going to show you how to design a complete module system, because there are a lot of design choices to be made after you've taken the technical hurdle of polymorphic values. So how do you export types from modules? How would it look like? So the types would still be a phase separation, so you can actually statically determine that. But that's something I'm not going to go in during this talk. I just want to show the technical hurdle of polymorphic values inside records.
I'm just saving expectation level.
Yeah. So yeah, put it a little bit down, and then. But I actually have a lot of ideas about it, so we can do that another time.
What is the difference between first-class records and records in Haskell or ML?
I have a lot of slides about that too, but the big difference is that in Haskell and ML, in Haskell you have to declare them before you can actually use them. So you can't just create a record. In ML you can't use records polymorphically, like polymorphically extend them. So they're not precise about what it exactly means, but there's a paper by Mark Jones about the T-Rex system, and there they make it precise. So they're exactly those records which would lead to predicates at runtime. Well, but I'll show slides about it. So so I'm going to talk a little bit about why it's important. So I'll give a few examples where I want to go to, and then show how to take care of these two challenges. So records. So in principle, you don't need records. If you just have tuples with group data together, you're done. So you can just say, a triple of 77 and 1973. That would be good enough. But it's much nicer from a programmer's point of view to give labels to these components. So I can write records with curly braces. And it's it's much more readable. You actually understand suddenly what it means. It's much safer because the day and month are distinct. It's a good thing for Europeans coming to America. And it's an abstraction from order, so it's a good thing. So now you could say, well, I could make a module suddenly. So if I would have these records and I could just declare them, you could suddenly make records with functions in there. So here's a little example of that. So I first give a type to make it easier to read, and I say, well, a type complex that's parameterized over types alpha has two constructors, Cartesian and polar, which take two arguments, floating point arguments, and construct such a complex number of type alpha. And I can, for example, get the real and imaginary part back from it, and there might be hundreds of other things you might want to do with complex numbers. And now you can easily package them up as a record. So I could make two implementations, for example, of these complex numbers as records. And I just give an implementation, one in terms of Cartesian coordinates and one in terms of polar coordinates. So now you would have little records with functions in there, and a lot like modules. So this is a lot like a module which has fields in it like Cartesian and polar and real, and there are functions in there. You can just select from it and use it, and I can make instances as many as I want in the normal scoping rules available. So this is very much like a module. But
sorry, I'm a bit confused about the type variable alpha. So can you tell us the types of cards?
Oh yeah, so both of these modules would have type complex float. So both of them represent their complex numbers as tuples of floats. So the alpha is the implementation type that's exposed here. So the alpha is really saying, I will, implement complex numbers as, tuple of floats. But, maybe you have a better way of implementing it. So this is not about data abstraction or anything. This is just about saying, you can have, instead of having a file with functions in there, you could just as well have a record with functions in there. This is something you can almost do in ML or Haskell, except they don't have records that you can just use like that. You have to declare them beforehand. So there's somewhat more that you can do. It kind of starts to look like first-class modules, because these records, you can see them as modules, but you can just pass them around and use them as arguments. So for example, you can say, well, given a complex number, I can construct an arithmetic module or record. So arithmetic would have two two labels plus and 0. And given some complex C, you can just construct a new record which has these functions in there. So
Okay, I'm still confused. I mean, you can, in ML, you can have a polymorphic record type the way you've shown.
yeah, definitely.
So I can write all the stuff that you've written so far, I can actually
Yeah.
write.
So in ML you can.
So what is, I'm a little confused about what.
Oh, okay. So I just wanted
Are
to
you
show
just
you.
giving background, or you're not yet talking about things you cannot do that you can do? And you
No,
wanna
no.
do?
So the next slide will actually show why this is not yet good enough.
Okay, good.
So Manuel's right. So in ML you can actually do this. You can't do this in Haskell, but in ML you can do this. So what is really lacking? Now, well, that's really the polymorphism. So you can't really put in any function there that you would like to do. You can't put in polymorphic values. So now, for example, if you want to make a somewhat more complicated module, you'll easily get to the point where you have polymorphic values in there, like an identity function, or the single function that I showed before. And the types of these, for example, the identity function, polymorphic value. It's for all alpha, it goes from alpha to alpha. And for the single, the same. And you can't abstract from that. So in ML, you can't write this because records just can't have polymorphic components. And that's a very fundamental restriction. That's not easy to solve at all, because it has to do with the first-class polymorphism. And this restriction, so this is kind of a small example where I show that this is a important restriction if you ever want to do modules. But actually, if you want to do true and proper abstraction, you'll hit it all the time. And it's for a large part a point of scalability and of writing libraries. So it doesn't show up that much, but when you need it, it's essential. You can't go around it. So it's a very important obstacle. For example, doing first-class modules in functional languages. So ML has a whole different language, actually, to talk about modules, and Haskell just hasn't bothered at all and doesn't have any kind of serious module system. So I think there's a big problem, but recently we can solve it, so I'm going to show that. Another thing which I haven't showed here yet is about the records. So I talked about first-class records and extensible records. And I think it's interesting to see that over here. So here I have this module I could pass as an argument, like the prelude, and I use a single function from it. If I would just write this, you could say, oh, I give a type signature. I say, well, I need a prelude as an argument. But you could also just look at what the type system would infer, and it would infer something like this. And I would say, well, for any record that contains a single field of type, alpha to list of alpha, and maybe more, so this is the extensibility. The R says for all R, so there might be more in the record, but it must have at least a single field of this type. Then I can, assign this type. So it really means that it gives you the minimal type signature, structurally, of what you expect from the argument that gets passed in. So, give me a second. So, I think this is very much like why structural equivalence is important. So many languages nowadays use nominal types, where they say, the type class name determines what comes in. You can only write prelude or some class name. But here we're looking structurally actually at a single member or single field called single with a certain type. So we get the minimal type necessary to make this correct. I think that's really important. And that's what dynamic, we go to a conference about Perl or Python. They have these notions, they say, well, if it looks like a duck and quacks like a duck, it must be a duck. And I think this is what they really mean. They're saying, yeah?
Have you compared this with C++? Because I think C++ templates actually have very similar semantics. No?
As these kind of records, or?
Yeah, this kind of inference where you have some reference to some particular thing like the single function here, and then basically the requirement to instantiate this kind of internal context is that the single must be there at some arbitrary rest or so. That looks to be very much
it's very much like that.
Nicer, but it would be capable to express C++ template in a more clean
Yeah, you can do a whole lot with So
Yeah.
with C++, I think with C++ could improve the whole lot. But with templates, you can do a lot of similar things. Yeah, that's for sure. Yeah?
So standard ML will infer types like this. It just requires that after type inference is complete, they've all been resolved statically.
Yeah,
at some
yeah.
point.
So yeah, that's right. So you can't really be polymorphic in the R. Yeah.
Excuse me. Doesn't OCaml have a similar thing to this, where you can actually type things like that?
So yeah, OCaml is similar, but it's not like this. So it's still restricted in other ways, but it's very similar. So I can, but they don't have, for example, they still don't have the polymorphic values inside their records.
Okay.
And that's, I think, a really important
that you can do,
distinction.
right? That thing there you can do, even infer it.
The little one here, you can, kind of.
Yeah, there. It's, it's 3 points, I think, but it's the ER is there.
Yeah, it's very similar to this. So you can do that thing in OCaml.
But all your records have to be named in OCaml. I don't see how you could do it.
Yeah, so
No anonymous record types.
So the labels are tied to a particular record type. There's no.
I think you were talking about the labeled the variants, right? To encode this.
No, that you can just say that the type you need to, for example, for a parameter, you can say the type is any class that has a single method.
But that's,
and whatever else.
Don't you need explicit casts at all the callers then?
I don't think so.
You're talking about the object part of OCaml.
Yeah.
Yeah, they have first
Right.
class polymorph.
Right.
Yeah. So but there must be declared the classes. So it's not like
I think they can be unnamed, like
no, but
any
so
class that has.
when you pass something, in the end
Oh.
you have to declare your classes with their fields and with their
At
things.
some point.
They're not first class values, right? So you can write functions that can actually do this, where you say I only depend on this member, and that's a huge that's a huge thing compared to normal object-oriented languages, where you have to decide beforehand as the designer. You have this big tree of objects, and you can no longer mix these two, even though they're the same kind of methods there. Okay, so that's really, that's my goal I want to reach. And actually, the examples I just showed, they're all typable and stuff in Morrow. But there are some technological hurdles to be taken before you can actually do that thing. And people say, well, it's kind of similar to this in C++ or to this in OCaml, but none of these things really support it on a fundamental level. So they all have their restrictions in strange ways. And the same with Haskell. It comes a long way, but it doesn't do the full thing. And that's so I'm going to talk mostly here today about the first class polymorphism, what that means in predicative and higher rank, and how that's being solved, and a little bit about first class records and variants if there's enough time. And the first class polymorphism is the one that allows me to put polymorphic values inside components, for example. So, why does it work in Hindley-Milner? Well, because there are two restrictions in Hindley-Milner, which doesn't make the polymorphism first class. So, there are two simple. Function arguments are never polymorphic. And to ensure that all types look sensible, all quantified type variables cannot be instantiated with a polymorphic type. They're only monomorphic types. So any argument you give will be monomorphic. So if you look at it, I'm going to look at the first restriction, and that's where function arguments could be polymorphic. So I'll give here an example of a function which takes a polymorphic argument. So the function 2 takes an argument, which I call choose here, and that argument can be used polymorphically. You give it two arguments of the same type, and it will return one of them probably as of that type. So inside the body of the function, I use it once with integers, and the second time with booleans. Right, so this function must really be polymorphic for all alpha, or otherwise I can't use it first with integers and then with booleans. It would just be a type error. So here's it's a really small example of a function. It's not very useful in itself, but you'll see it over and over again when you write libraries or want to abstract from common idioms. So we call this a rank 2 polymorphic type. And that's something that's not supported in Hindley-Milner. All types in Hindley-Milner are rank 0 or rank 1, but not above it. So as soon as you go to higher ranks, then I've explained part of my title, That really means passing polymorphic values as arguments. So here's a formal definition of what a rank of a type is, and it's actually very intuitive. Just count the nesting of the for alls in your arguments. So Haskell actually supports this as one of the few languages around. So as soon as you give an explicit type signature, you can actually use this. That's nice. People were almost saying that it supports first-class polymorphism. But when you play with it, you actually hit the second limitation of Hindley-Milner. And that's the second, another part of my title, the impredicativeness. And that means a system is predicative if a quantified type variable can only be instantiated with a monomorphic type. And that was the second restriction from Hindley-Milner. So as soon as you be impredicative, it's the other way around. You can actually instantiate type variables with any kind of type. And that's what makes real first-class polymorphism, lifting both restrictions. So Haskell is kind of like halfway there, but not yet there. So here's an example of that. So I have the single function again that puts an argument in a list, and the identity function. And now when I type single ID, I kind of have a choice. So one thing that Haskell will always do is say, well, I'm going to instantiate this for all beta, so it will be some function from gamma to gamma. And then I can instantiate this type variable alpha with gamma to gamma. And we end up with, for all some type, it's a list of functions from that type to another type. Does it make sense? So this is what Haskell will say, but there's actually another type you could give to it, which is also very sensible. And to show you what the other type will be, I will actually move, quickly to system F, so you can actually where we make explicit about how types are passed. Now, system F for me that's like the gold standard. It's like you can't do much better than system F. Well, not very much better. So I'm going to pass types explicitly, and I'm going to do it so I can show you actually how you can give different typings to the single ID function. So over here we have, for example, the increment function that would be explicitly typed now. So you would say, well, it takes an argument x of type int and add 1 to it. And the identity function would say, well, it first takes a type argument alpha, for all alpha, and then an argument x, a real argument x of that type alpha, and it will return x. So we make explicit how we pass the types with the big lambdas over there. So now we go with a single ID. And now suddenly in system F, which is an impredicative system, I can give two types which are equally good. Well, they're not. So one of them is actually better than the other. But so this was my first one that I showed you. This is what Haskell would do, or ML, or any other language. So it will say, well, for all gamma, it will instantiate single with gamma to gamma as its argument, and the identity alpha with gamma. So you end up with this type. But in system F, I have an extra choice. I can actually instantiate the type variable of single with a real polymorphic value, namely for all beta, beta to beta. And I get a list of polymorphic functions. Now there's a big difference between these two types. So the second one, the list of polymorphic functions, means I can use each element of this list polymorphically. So I can use each element, I can first apply to integers and maybe later to booleans, and because it's really they're all polymorphic functions. But with the second type here, for all gamma, list of gamma to gamma, as soon as I pick out elements and I use it, for example, for integers, it will be fixed for integers, because these are not polymorphic functions in there. You can only instantiate it once. And then they will all be for the same type. Rolf?
Mark P. Jones, first-class polymorphism, of course, allows you to encode this, well, just in the same way. You just have to invent a constructor, right?
Yeah. So you can do, a similar thing again. Like C++, people kind of try to get around these limitations. So they, for example, in Haskell, you can actually pack polymorphic values using constructors, and then you have to pack and unpack them all the time. But that's really just that's like circumventing the problem to do some kind of first-class polymorphism, but it doesn't solve the real goal. The goal is not having first-class polymorphism. The goal is having nice abstraction for the programmer. And as soon as you have to do the packing and unpacking, the whole abstraction level kind of falls down. For each specific type, you have to introduce a specific constructor. And I think as soon as you want to write real libraries, it's just not working at all. So that's in response to your...
Just easy question. Can I think of predicative types as being the ones where the for all quantifiers has been lifted all the way to the top, and then impredicative types as ones where it can appear further inside?
Yes.
It still appear inside. Okay.
No, that's really, so what you're talking about now is really the higher rankedness.
Okay.
So when the for alls are on the side, it's rank 1. And when the for alls are also inside, you could think of them higher rank.
Okay.
Impredicative means I'm going to instantiate a quantified type variable. Well, if you look at the single type, it's quantified over some type alpha. But in a predicative system, this alpha can only be a monomorphic type. It cannot be a type scheme for all thing itself.
Right.
I cannot make a list of for all beta, beta to beta here. But in an impredicative system, you can, because I pass a real polymorphic value to the for all alpha of single. So that's a really important abstraction mechanism. But now is really why didn't people do that? Because it doesn't seem too hard to actually extend it. Well, it is really hard. So there have been lots of technical papers about how to actually circumvent it or to kind of go there. And this is the real reason. This is like the core why it's difficult. Because there's some undecidability question. And here's an example of that. So you have to think really hard if you want to figure out the types here. But I'm going to look at the application choose ID. So I give one argument here for the alpha, the identity function. So I get back a function from alpha to alpha. And I really have a choice in how to instantiate this alpha. I can either do the thing that Haskell would do, instantiate and then generalize. And I would get for all gamma, gamma to gamma, gamma to gamma. Or I could leave the alpha as polymorphic value, impredicative, for all beta, beta to beta. So I get a function that takes truly polymorphic values and returns a truly polymorphic function again. Now here's a troublesome situation suddenly, because these types are incomparable. Neither one is better than the other. And you cannot, you can't pick one at random like Haskell is doing now. Haskell takes the first one always. Well, random is a big thing. It always takes the first one. But it might not be the right choice for you. And you don't want the user to annotate all these terms. So you have a problem in choosing which one to use, and neither of them is better than the other. So why is neither of them better than the other? Well, because one of them, this one, I could, for example, pass a function from int to int. That would be okay, and I would get back a function from int to int. That's great, so I can use it. But the second one, I have to put in a truly polymorphic function. So I can't put in int to int. Must be something like the identity function. But I get something more back too. I get, namely, a really polymorphic function back, not just for int to int. So there's a real trade-off to be made here. Now this is a simple example, but there are many bigger examples where this also holds. So what type do you choose? Well, that's really troublesome. So people have been thinking a lot about it. And it really comes down to finding principal types, as we call it. So principal type is the best possible type you can find. And here, as my previous examples show, it's hard to find the best possible type. And you really want your type system to have principal types. It means for each expression, I can find the best possible type, a principal type. And I just gave you an expression which is hard to find the best possible one. Now this is really important, so you have actually modular type inference. You can look at a little part of your program, infer the types, and be sure this is the best one. Never have to look back again. And this is actually, how do you call that? You need it for efficient type inference. So, Hindley-Milner has principal types, but Haskell with impredicative higher rank types won't have that anymore. So there's the big, why no one did that. And they've already think about it since the 90s, as Rolf was saying with Mark Jones' paper. But fortunately, there's a real smart people in France. DJ Le Baudlin and DJ Rémy. Maybe it's the name, right? It's a good combination. And they did, I think, really, so DJ Le Baudlin is a PhD student of DJ Rémy. And I think DJ Le Baudlin wrote a really impressive PhD thesis. that solve these hurdles. So it's also hard to read. So one of my missions is actually say how great this work is, and try to explain it in layman's terms.
So it's a tool that the inference problem is then solvable once you have these annotations for the function arguments. Is that the only problem with the higher rank types, or is there also?
So if you have annotations, you can do higher rank types.
I mean, if you had your example with choose before, no? If you just would tell what interpretation of the function you want to have, polymorphic or monomorphic, no?
Yeah.
You need two types.
Then the inference problem, after you have told that information without explicit typing or so, then the inference problem is solvable. Or?
So as soon as you give the explicit types, you can actually infer types for higher ranked, or you can check higher ranked types, but you still can't do the impredicativeness because you just can't assign a type to choose ID. You don't know which one is the best. So even when you would write it down, you still have to make a choice, which is arbitrary.
You would always have two variations.
Yeah.
It's clear, but suppose you make a choice for the variant you want to have. No?
Oh, yeah.
Then the inference problem is solvable.
No. So
isn't there still a higher order unification problem?
there's still a problem. Yeah. So if you would do, it's still not solvable. Yeah. There's still you still run into unification problems. But
Well, I'm a little confused. I mean, if you give explicit instantiations, then it is just checking, right? Is there still
You just say which interpretation you want to choose, a polymorphic one or
no?
not,
But if you
without
take
giving
system
the type.
F, right? I mean, and I give.
So if I
all these
give
type instantiations,
annotations at also application sites,
yes, exactly.
then you can check it. Yes.
I think that's
Then
what
you
we
end up with system F, and in practice, that's really hard to use. Like the burden is too great to actually use that. So that's I think that's absolutely right. So with MLF is they make an extension of Hindley-Milner type inference, a theoretical extension. It's very solid theoretical piece of work. It doesn't have it takes a while to apply it into a more practical setting, but it has higher rank polymorphism. It's impredictive. And has principal types. Wow, that's great. That's exactly what we wanted. It was actually presented at ICFP in 2003, but it didn't got much attention somehow. And I think it's really because it's hard to access the work. It's very lots of proofs, lots of theorems, and but I think it's great work, and it should be more widely known. So I'm going to show you how MLF works and how they solve this problem of choose ID. So the types of MLF are sketched here in a little. So I have monomorphic types. This means type amplification to a constant, and the gamma should be a C or something, a constant, a little error. And for example, type application might be the function arrow or lists or something. And we have type variables. So these are monomorphic types. So there's a strict distinction between monomorphic types and polymorphic types. And then we have sigmas, which are type schemes. So we have a most polymorphic type, which we call bottom. And we have normal polymorphic types. Say, well, for all some things, Q, a prefix, and I give some monomorphic type. Now that kind of looks strange, because you would expect with higher rank types that in here there could actually be higher order, quantifiers. But that's not the case. We clearly separate this out. And the prefixes are made in a special way. Namely, they look like this. Alpha, diamond type, alpha, diamond type, alpha, diamond type, for all. And this really means for all alpha. And the diamonds are either the two kinds of bounds. And that's either a flexible bound or a rigid bound. A flexible means it can be any instance of, and rigid means it must be at least as polymorphic as this guy. And I'm going to give examples from it, so don't be afraid yet. So the good part is, there's a very good notion about what it means when one type is more polymorphic than the other.
Can you go back? So I would expect that the first line to see sigmas there as arguments to the type constructor, because otherwise, yes. How can I have
higher rank types?
Higher rank types.
Yeah, right. That's exactly right. So the higher rank types will be bound in the prefix. And that's, so I'll give you an example of that right over here. So, well, I'll come to that.
I'll wait.
Yeah. So one thing I think is really nice is it gives a very nice ordering on type schemes. It really says, what type is more polymorphic than the other one. So the most polymorphic type would be bottom, and then this relation which says, well, and this guy would be somewhat less polymorphic, but also very polymorphic, namely, for all A to A. And then int to int would be even somewhat less polymorphic, but it's still like instance of these previous guys. So the last ones I've added, because it's work I'm currently working on. Then you would have existential types, and then in the end you would actually have top, the least polymorphic type. So this is actually really nice. There's a very nice theory surrounding this all. It gives where you can, work on without looking at algorithms or actual implementations. So that's really nice. Well, of course, our type of choose ID is not an instance of the other. So here's a, but not. This won't be true. So there's really a difference between those kind of types. Okay, so here are some examples, practical examples. So here's the type of the identity function. For all A to A. But I'm going to add a little bound, because it's an MLF type. I'm going to say, well, this alpha here, it can be really, I'm okay with it as long as it's better than, the most polymorphic type. Or the same. So basically I'm saying it can be anything that you can pass in here and use it. So normally I abbreviate this thing as alpha. So I can just write, my usual types again. Yeah.
The bounds were taus, so bounds can have polymorphic types?
Yeah, definitely. So over here, these are sigmas at the bounds. And that's how you get the higher rankness. So if you look here, for single ID, for example, we had a choice to make. We could.
On your slide, you had a tau. That's why we were asking about it. So if you go back to slides, you'll see.
Oh no. Oh, that's really bad. Okay. Well, let me correct here for the web people. These must be sigmas. Yeah. Okay. Sorry. Wow, that's a bit confusing. Okay, never noticed it. I've already used this slide 2 times before during other talks. No one saw it. So. Had I lost the audience, or were they just, so smart that they just saw there was sigmas? Never know. So, yeah. So those should be sigmas. I'm bounded by sigmas. So that's why I can use bottom here. So that's really essential, because now I'm going to delay my choices. So I give a few examples here of higher rank type. First, the to function. We remember that. It took a really polymorphic argument. For all A to A to A to A, and then it gave an int bool tuple. But now I see I just use alpha here, and I'm going to bind the higher rank type in the bound. So I'm going to say it must be at least as polymorphic as this function. So I use a rigid bound, the equal sign. Now sometimes I can actually choose. It might be as polymorphic, but maybe not. So for example, with single ID, I would get a list of alpha, and the alpha is, as polymorphic as, less polymorphic or as polymorphic as for all beta to beta. So I can still choose. I can either choose, I'll make it a list of truly polymorphic functions for all beta to beta, or I'm going to instantiate it. And that's how we get around with the choose ID. We get this type. So we say it's really a function from alpha to alpha, but we delay how we're going to instantiate it. So we're going to say it must be an instance of this type. And now both our choices are still possible. So if you look at the instance relation, you can actually see that this type would really be an instance of this guy here. And the same where I instantiate on the outer side. So now both types is where it used to be a choice. Now I can actually give a best possible type suddenly to my choose ID expression by kind of delaying the decision. So it's bound in the constraint. Now this all looks, especially when you look at the theory, it looks really complicated because of all these bounds, and you can't really read it that easily anymore. But there's actually a heuristic you can apply, which makes them suddenly a lot more readable, and only when it's essential, it will actually show up. So actually in Morrow you can write normal types, like here single ID will just be a list of for all A to A, and 2 will be written like this, so it will be looking natural. All Haskell programs will still look the same. Only at the point where it becomes essential, you'll see these bounds popping up. So with choose IDs, it's essential, because there's a real choice to be made, and you can't You can't decide yet at this point in time. But if you do these things, you actually there's a whole algorithm and there's decidable unification, and you can actually use them as you want to. And this is the heuristic. Well, it's something that's by intuition true. It's something that only by looking in practice you can say, oh, this is a good thing to use. So it's a heuristic. But up till now, the practice we had, it looks really good. So we do get all the benefits of the MLF system without showing the complexity back to the user. And once you have it, you can actually get all the other things for free. So the example I showed earlier of the polymorphic functions inside data structures, you just get them, and you don't have to do extra work to use those. And other things that are really important is that a lot of laws that fail to hold, in Haskell, for example, still hold again. So you would expect, for example, that if you write 2 choose, so this is a higher ranked application, because 2 really needs a polymorphic argument, that you can also write it like this, because you can always apply the identity function to something. Well, in Haskell, this won't work, because suddenly the type stream is basically extended as more like a hack. But within MLF, these abstractions, barriers, doesn't exist, so you can still use proper extraction and use your proper laws. It's really nice. And you can go like, all the way. I won't go through that example. It's only for the, functional inclined among us. So I can actually show a few examples of that. That's really working. This might be fun to see. So I made a little. Can everyone read that? What? I made even a color interpreter. It takes a really long time to run, but it's written in Haskell, so it's not my fault. No. Next time I'll use F# and it will just race through it. You'll never. So you can write things in here like give me the type of the identity. It's for all A to A, or give me the type of choose. Well, or I can write little lists. So I will actually evaluate this thing, or take the sum of the list from numbers from 1 to 10. Okay, so it does its normal things, but actually it has this polymorphic type system. So for example, I can write the list of an identity function, and we'll write type, and it will indeed infer that's a list of really polymorphic functions. Not and when I suddenly add something to it, like a lambda abstraction, it will still know that it's. Well, it will. What is it? Oh, okay. I should read the error messages, right? It will still know it's for all A to A. So there's truly proper abstraction. And now the big thing is, of course, what if I would add a function that would add a number to it? So I'll add a function that adds a number, and then we'll actually see. Oh, I need to instantiate this thing. Now it's just a list of int to int only. Other things you can do is, so I can give a little example of that. So this is a really interesting function. It applies a function to itself called auto. It takes a function f and applies it to itself. So what will happen? Oh, it doesn't work. So why does it work? Well, because there are many types you can actually give to this, and you have to help the type checker a little bit. So sometimes you have to annotate function arguments, namely when you use them polymorphically. Well, that's happening right now. So this is one of the types I could give to the function. I have to say, well, the f must be really a polymorphic value for all A to A. And then it will actually return you a really polymorphic value. Oh, that's great. So, it's...
Is this what you're showing here with the self-application? Is that an instance of the that it's not completely inferable in your system, or?
Yeah. So you can't infer. So maybe I wasn't clear about it enough. You can't infer types for an impredicative higher ranked type system in general. Mm-hmm. So the rule is that you have to annotate arguments, only arguments, of functions whenever their arguments are used polymorphically. That means within the body, I use it at different instantiations. So that's happening here with the auto function. But the thing is that in practice it hardly happens. Only in your library procedure where you really do the interesting trick. So the annotation burden is still really, really low. But that's exactly right. So it's undecidable in general if you don't have these annotations. But it knows when it's undecidable. So it's not like it will not decide. Okay, so here we have the auto function, and it takes really polymorphic arguments. So I can, for example, type auto ID, but I wouldn't. So let's define a function increment. It's int to int. I wouldn't be able to type auto int inc because increment wouldn't be polymorphic enough for the auto function. It would start complaining. And of course, all my usual abstraction mechanisms keep working. So if I look at a map function, does everyone know the map function? It maps a function over a list. So it takes some function from A to B, and it takes a list of A to a list of B by applying the function to each element. So one thing that you can't do, for example, in Haskell or other functional languages would be this. So the ID would be a list of polymorphic functions. So the auto function, I can apply it to this list of identity function if I want to. But now it really means that I'm having polymorphic value in here, and I'm having a function that really takes polymorphic values, auto, but I'm using it with a standard library function which doesn't know anything about polymorphic values. Well, it doesn't matter. So MLF will actually abstract everything in the right way, and it will all work out. I'll show you right there. Not much will happen actually, but and I think that's really important. So I can define my abstractions once, like map, get the best possible type, and use them at all possible values. If you look at Haskell or other extensions that try to achieve this, they're all limited. So you have to duplicate basically the map function for each polymorphic value you're going to use it. And that's, I think that's a big thing. Then of course, so I'll show a few more functions. So you can, for example, put things in records, right, and or a constant function. So you get, a record with an identity function and a constant label. So look, the constant function is actually really interesting for the, the functional inclinedness. You would expect for all A to B to A. But, we're inferring the best possible type. So we are actually inferring for all A, and then we get back a function that says for all B to A. Although these are eta convertible in system F, so it's not completely.
This is an exception of Morrow, you said,
no?
No. Oh.
No, this is an experimental system to explore the boundaries of type inference.
So my question would have been actually then how it interacts with constructor classes, but that's...
Okay, well, that's really interesting because, so if you want to use this in Haskell, you need to have qualified types. And it's completely not trivial to do that. So that's actually where I come in. Wow, I anticipated the question. Look at that. So the question that Wolfgang was asking, how does it interact with constructor classes in Haskell? And it really, in general, would mean how does it interact with the theory of qualified types? So this is the qualified types. You give predicates over your quantifier. So instead of saying for all alpha, this is a function from alpha to alpha to alpha, you say, well, for all alpha that satisfy the number predicate. And in Haskell it would mean that are in the number class. So we're really talking about everything that can be considered a number, like that has a plus defined, for example. There would be float and int and a lot of things, but not all types. It would be a restriction of all types. And that's the theory of qualified types. Is a general theory, which also includes the type classes of Haskell as a special case. So this would be the type that would be inferred in Haskell. And the question is really, how does this interact, these predicates, the qualified types, with MLF? That was an important question for me because I'm a real Haskell guy, so I wanted to make sure that it works out. And generalizing the theory of MLF to qualified types is relatively straightforward. That was very nice because it was very pleasing from a theoretical perspective. But to implement such system, you have to do a runtime translation. So each predicate, like the number, must be passed at runtime with evidence. And that turns out to be really, really tricky. So actually, Simon Peyton-Jones has written about it in his paper about hiring types. And he wrote, together with Mark Shields, he wrote a little remark that, well, if you have impredicative types, things are going to be really hard from an implementation point of view, and we don't think it can be done. And I actually thought for a long time the same, but we were wrong. So we actually found out there's a very nice type-directed translation. And I've written a paper out at Anders Leu. It's qualified types for MLF, and it generalizes this whole theory for MLF types. And hopefully also will make MLF more popular by giving a nice introduction to the system. So that's we're going to present that in end of September at ICFP. So whoever is there will be.
So you really need to change your theory. You can't just encode the bounded types using your theory.
No. So MLF, as soon as you move into qualified types, you really you're doing something different with the alphas. They're not just bounded by another polymorphic type, but they're really part of some other predicate which you can't decide upon.
But you just add extra parameters that have all the functions that you need to operate on them?
Yeah, you could look at it that way. Yeah, so there's normally, at the runtime, they call it evidence, but for example in Haskell, it would be dictionaries. And there would be a bunch of functions that give the implementation for plus, the implementation for 0, and then you're in the number class. So the implementation can actually rely on this dictionary to call the right functions. So as soon as you move into impredicative types, you get into a lot of trouble that you have to, if you do it naively, you have to traverse data structures, and you can't do it in general. So you have to be, actually what we're passing are evidence transformers. But I think it will go too far during this talk to go into the technical details. So this is really what I wanted to talk about, but it's this is about technical depth that we'll go to. So I see I'm actually already running out of time. I'm supposed to talk for an hour. So I had a lot more about records, but I think I'll just skip through them, right? Or how is that? Should I talk for 1.5 hours, or?
Probably if you can conclude, and then people can take.
Yeah, that's a good thing.
Talk to you since Daan is here for 2 more weeks, so there's more chance for interaction.
Okay, so I'll skip quickly through my record slides. So you see, I worked really hard on them, and showed that there's so many things you can do with records, and restriction and update and rename, and they're all safe. And wow, there are lots of choices you can make. And this is how the French people do the records. That was your question about objects, and you can go really difficult, but we do it really simple, and that works also well. And I've written a paper about it, so you can read about it. And oh yeah, there are also variants, and oh great, first class patterns. So now you can actually, with just these 2 things, you can actually even encode if without having anything else. And that's the end of my talk, and I really hope you enjoyed it. And next time I hope to, schedule it better with just 30 slides instead of 50. Okay, thanks a lot. So I'm here for another half hour where I can answer questions, and I even made copies of a few of my papers, so you can, if you're interested, you can actually read it here. Thanks a lot.